Charles' law, another scientist, who came up with the idea of relating volume and temperature. Charles' law can be stated like this. We can say that V1 over T1 equals V2 divided by T2. Just like Boyle's law, Charles' law, when expressed like this, assumes that some sort of change happens in our gas sample. And the volume over the temperature before the change equals the volume divided by the temperature after the change. Now, we talk about volume and temperature here. Whenever we're using temperature with gases, I'm going to do this in red because it's so important, we must always use the Kelvin temperature. Must use Kelvin temperature. We always have to do this whenever we're using temperature with gases. Now, if you remember earlier, the Kelvin temperature is found by taking the degree Celsius temperature and adding 273 to it, and then we get our temperature in Kelvin. It's not degrees Kelvin, it's just Kelvin. Keeping that in mind, let's go ahead and take a look at this problem. We say that a balloon takes up 625 liters at 0 degrees Celsius. If it's heated to 80 degrees Celsius, what will its new volume be? There are a couple of steps that we have to take. Let's figure out which of these variables we're going to be solving for first of all. There's a change. We change this gas by heating it up. So before our volume, 625 liters, we have that, and our temperature, 0 degrees Celsius. But remember, we're going to have to change this to Kelvin temperature before we can use it in the equation. If it's heated to 80 degrees Celsius, so we know what the new temperature is, but remember, we have to change this to Kelvin. What will its new volume be? So V2 is going to be what we're trying to solve for. First of all, though, we're going to have to change these Celsius temperatures into Kelvin temperatures. So T1 equals 0 degrees Celsius plus 273 equals, well, this one's easy, 273 Kelvin. That's our T1. T2 is going to be 80 degrees plus 273, which is going to give us 353 Kelvin. See, these are the two Kelvin temperatures that we're going to have to use going into this. Now, let's see how we can rearrange this equation here. We know this guy, and this guy, we're solving for V2, so we're just going to move T2 up here, as if we're multiplying both sides by T2. So our equation is going to become V1 times T2 divided by T1 equals V2. Let's go ahead now and plug these values in. V1, our initial volume is 625 liters times our T2, which is, in kelvins, 353 Kelvin, divided by T1, which is, always use a Kelvin temperature, 273 Kelvin. Let's look at what happens to our units here. The Kelvin cancel out, so our final answer is going to be left in liters, and the answer to this is going to be 808 liters, rounded to 3 significant figures.